Designing a filter. The basic operation of a filter is to remove unwanted frequencies from a signal. So in this case, we'll be removing the noise from our signal because we want a better, efficient output. We'll be using the IIR filter. We'll be designing that and we'll filter our signal through that filter for this purpose. IIR filter is more quicker and it's more efficient in terms of the filtering operation. So these will be the signal specifications that will be put in MATLAB, in LabVIEW, so that we'll be able to generate our signals. So I'm going to open LabVIEW. This is a block diagram of the two signals combined, and they're added to get the numeric output, just to indicate the values, and we'll be showing the graph of the output and the frequency spectrum of these two signals. This will be the while loop, having a for loop inside that will control the number of samples that will be transferred into our signal input. And we're just going to run this to show you the output. This is the output. Well, we have a frequency spike. You see a major spike at 180 and 225. We had our frequencies around there. At 180 was our signal for the input signal, and then there's a noise signal at 225. Yes. So I'm just going to show the calculations of this operation. You need to calculate this for the Botter plot. Botter plot is very important to be able to get the transfer response of your signal. But before that, we need to get the pole and zero placements that you're going to include inside the complex diagram, just to see where your poles and your zeros are lying. I'm just going to show the calculation of the poles. This is the formula that is used. Very easy standard formula. 180 because for the signal it was 180 frequency. Then 500 is sample frequency. The opposite side and the adjacent side of your pole. Then you get your two poles lying on the. It's on the left hand side of the complex plane. Then you calculate your zero, same formula, just using the 225 for the noise and the 500 something frequency still the same. Solve that all together, then get your transfer function equation. Transfer function in order to be able to go and plot your Botter plot. Solve it as shown. I solved the numerator and the denominator separately, then combine them to transfer them into the original equation. Just before you times it by z negative squared over z negative squared, I'm going to show the Botter plot of the output. So I'm going to go to MATLAB coding. Okay, this is the Botter plot. You can see that it's decreasing and eventually approaching zero. It's like a low pass filter, if one can say. Yeah, the IIR filters, and this is the frequency response of it. But I have a better output showing I used Excel to show the better output. This is more clearer, showing the actual decline of the response, and eventually it's going to approach zero. While looking at these, it's in radians per second. Our 180 is lying somewhere there, and 225 is somewhere there. It won't be clearly visible. It looks like these signals are equal, even though they're not, because of the range difference. Obviously, when you times 118 times it by 2 pi, times it by 2 pi to get the radians per second, you'll see that it's lying somewhere there. It's 1130 something, and then the other one is somewhere there just before 2000. So there will be the Botter plot response of your signal that is generated. After that, we need to design the IIR filter. I'm just going to show the structure in LabVIEW. Show the structure in LabVIEW and show the outputs of the signal. So this is the structure. Before we go to the structure, I will show the calculation, the final coefficients for the IIR from the transfer function. After multiplying it by that, you get that. Then these will be the coefficients. Looking at this structure, I just want to show B0, B1, and B2 will be your numerator coefficients in that order, and then the negative A1 and negative A2 will be the denominator coefficients. So it's going to be negative 0,902, and then it's going to be negative 2,03. You should plot this into your IIR filter. Love you. Right, this is the IIR filter structure. This is how it looks. Have your timing there. This is how plot the values are plotted in, as you can see. And you still have that loop, control loop for the for loop, and your block diagram there. Okay, now these will be your indicators. Oh, it's just an indicator indicating your amplitude. This raw signal, the signal that will not be outputted, will be shown at the top, and the output of the signal will be at the bottom. This is the indicator for the input, this is the indicator for the output, just to remind. I'm just going to run this so that we can see that our signal is successfully filtered. This is running, and if you can just look at the two graphs, you can see that our signal is filtered. Noise is reduced, and looking at the indicator you can see that the needle is not moving very much on the output, and the graph shows perfectly that the signal is indeed it's reduced. It not necessarily reduced, the noise is removed, and you can see that our signal is successfully filtered. Well, it's just that it's moving around and we won't be able to measure the actual amplitude. It should be around 5. Should be 5. I'm just gonna stop. This is our signal. Output, filtered signal, the raw input signal. So you can see that our IIR did do the job of filtering the signal properly. Thank you.